satellites, and we've talked about this before. What kind of satellites have we talked about? We did a whole problem on geosynchronous orbit. Do you guys remember that? What's a geosynchronous orbit?
Rotates like the same as the Earth is rotating.
Right, so what is the period of a geosynchronous orbit?
24 hours.
24 hours, right? Because it's moving exactly with Earth. It's really far away to get a geosynchronous orbit. What do we know about orbits as you move closer to the Earth? Faster or slower?
Slow.
Faster, right? And we're gonna actually show why with energy this time, but before we were talking about centripetal force, right? Because an orbit is circular motion by definition, and usually it's uniform circular motion because you have a constant speed, but you're trying to stay the same distance at the same speed going around Earth, okay? So remember, the speed of a satellite we can calculate from centripetal force, right? So you have force equals mass times acceleration. What is the force? What's your centripetal force when you're talking about orbits? Gravity, right? It keeps things going in a circle. So we have our gravitational force, and then our speed comes from that. So force equals mass times acceleration says we have basically the gravitational force on one side, then mass, then our v squared over r over here. You can solve for v and you end up with something that looks like this. Okay, there's a lot of canceling that happens. But this means that the speed of a satellite in a circular orbit, this is constant, yes? What about this? Does this change?
No.
No, not for the object, right? So what this means is speed is always dependent on radius. So what we've talked about, like if you have a larger radius, what happens to your speed? Slows down. So closer things to Earth move faster than things that are farther away from Earth because they have to, okay? Because all of them have the same centripetal force, but if you change the radius, you change the speed, okay? So remember, we have these types of orbits. This is low Earth orbit. How fast are satellites moving here? Very fast. And you can, if you get a satellite tracking app and you look up, most satellites are moving pretty fast because you see them go all the way across the sky. Like you can watch them moving. That's how you know they're not stars, because stars don't usually move like that. And that means if you like just calculate like how far that is from horizon to horizon and the amount of time it takes to see them, those things are moving at a good clip. Okay, not even if you don't know their actual radius, you know they're moving pretty quickly. Just compare their motion to like how fast airplanes move, and they're much farther away, and it's circles or spheres if you want to think of it that way. So we have low Earth orbit, so the International Space Station is just zipping around. If you want to like feel uncomfortable about how fast things are moving in space, just watch that mediocre movie Gravity with Sandra Bullock. She should have died a lot in that movie, but it's fine. And then medium Earth orbit is this yellow area over here. This is where the GPS satellites hang out, so they're moving a little bit slower. This is where geosynchronous orbit is. It's outside of medium Earth orbit. And then out here, there's not much stuff out here because like you start getting towards infinity and it's harder for things to stay in orbit after that, okay? So remember, for circular orbits, these are bound. So that means that your kinetic and potential energy are tied together by the fact that your potential energy depends on distance and your kinetic energy depends on speed, but there's a relationship between the distance and speed that can't be broken, okay? So what this means is your kinetic energy is equal to -1/2 your potential energy. There's a whole derivation that we're kind of skipping, but don't worry about it. So if you add up your potential and kinetic energy, that means your total energy is just 1/2 of your potential energy, okay? Which is a little bit nuts. But orbital energies are cool. This is our kinetic energy, total energy. This is just graphing them, okay? If you take upper division mechanics, one of the coolest, like if you become a physicist and take, which is like none of you are probably going to do, but one of the coolest things in that class is they show you the effective potential, and basically it makes little like dips, right? And those little dips are the orbits, like going this speed means you can be in this kind of orbit. And so you'll find out that all of the orbits you can get are conical sections. So the types of motion you have with gravity, because of the way that this stuff works out, is you can be in a bound circular orbit, which is like most of the planets. You can be in an elliptical orbit, right? Then you can be in a parabolic orbit, and then you can be in a hyperbolic orbit depending on your speed and the masses, okay? So what that means is if something comes in contact with another large mass, it either gets stuck going around it. Well, I guess it could also hit it, but that's not like a conic. Do you guys know what conic sections are? No? Okay. So imagine a cone, like an ice cream cone shape, but it's solid. If you slice it across like this and you turn it, what does it look like? Circle. Okay? If you slice it diagonally and look at it, what does it look like? That's an ellipse, right? It's like, so slice it, get a circle, then you get like a squished circle, okay? If you take a bigger slice all the way through to the bottom, you can get parabolas and hyperbolas. If you Google conic section, there's better pictures instead of me just waving my hands at you trying to tell you what it is. But it's really cool. All of those like graphical representations are called conic sections. And those are also all the shapes of orbits when you talk about gravitation. Okay, and also particle collision. So any kind of like interaction with an inverse square force. Yeah? No? Interesting? Not interesting?
Yeah, it's interesting.
Okay, good. All right.